It's my great pleasure to present the next plenary speaker, Eric Fusy. Eric made his PhD in 2007 under the direction of Gilles Schaeffer and Philippe Flageolet. Soon he joined the CNRS as chargé de recherche. And for a long time he was at the École Polytechnique in Paris. And recently he was promoted Directeur de Recherche and moved to another end of Paris, to Marne-la-Vallée, where he joined the combinatorics probability group there. Eric is very well known for his beautiful work on maps. So maps is certainly in the center of his interests, but what his work is much broader. He is interested in enumerative aspects of combinatorial objects, exact enumeration, asymptotic enumeration, in particular bijections, but also in random and probabilistic aspects. So in his title, we don't see any maps, but the abstract promises that there are maps behind. So we are looking forward to your talk.
Thank you, Christian. So thank you for the very nice introduction, and thank you for the program committee to give me the opportunity to talk here, and the organizing committee for the very nice week here. So it's a great pleasure. And yeah, so I will talk about some recent joint work with Erkan Narmanli and Gilles Schaeffer. So there will be maps. And also, yeah, so since that was banquet yesterday, so maybe you're a little tired, but I can quite promise it will be not complicated, so I think it should really be quite easy to follow. And yeah, so as Christian said, my main topic is enumerative combinatorics and bijective combinatorics, and in particular on maps. So we have already seen maps in the talk of Adrien yesterday, so let me spend some time on defining these and motivating also why they are really well studied. So a map is a connected graph embedded on the sphere, okay, so up to homeomorphism. So they are really topological objects. So you can see that, for instance, the two first are equivalent as maps. The last one is different, so we have moved the loop from the face on the left to the face on the right, so this is not possible by a homeomorphism. So actually in a map, it's a kind of a graph where the cyclic order of the incident half edges to each vertex is prescribed. So it's a combinatorial object also in this sense. So in general, the maps can be considered on any surface or any genus. Okay, so I think we have some within talk. But here, for me, there will always be planar, so genus 0. And also for enumeration, usually we have a convention of deleting symmetries by marking typically a corner or half edge. Okay, so it will always be implicit in the result I will give that the map is rooted. Yeah, so in genus 0, usually you just draw a map in the plane, so you declare the face incident to the root as the outer face, and you project out of it to the plane, and then actually you can say a map is, yeah, maybe more simply, you can say it's a planar graph, so drawn planarly in the plane, and up to continuous deformation. Okay, so it's important, it's really topological. And yeah, so actually it has been very well studied since the work of Tutt in the 60s, where he obtained, so his starting motivation, he looked at the four-color theorem, so maybe he was looking at the enumerative side, like counting four-colored planar maps, so which was difficult, but then he obtained very nice results for counting rooted maps, okay? So it was not a bijective method, it was a method by deleting a root edge and writing a functional equation, as Adrien showed yesterday. So he solved it by guessing checking. And he found these nice explicit formulas with essentially binomial coefficients. So it's really reminiscent to twin formulas, but well, you have this 3 to the n, but also a factor, a little factor in front. And so so the method, so there was a school after TUT, so a lot of results have been obtained on counting maps. So they have been generalized in this work by Busquemelu and Jian, and we have seen also the further extension yesterday in Adrien's talk. And so in general, generating functions are algebraic for counting maps, and we also have this universal exponent for the asymptotic enumeration. So what matters is really the sub-exponential, so polynomial correction, and to the -5/2, which is really universal to map family. So you can consider like triangulations, quadrangulations, loopless maps. You will always find this n to the -5/2. Okay, so the c, the gamma will depend on the model, but the -5/2 is really universal.
Is n always going to be referring to the number of edges?
Yeah, good question. Yeah, so the question is n always the number of edges for families of maps? Actually, no, it's a natural size parameter. So for triangulations, it can be number of vertices. So things like that. Yeah. So, yeah, so then, of course, so the early proofs by TUT were not bijective, so there was really a motivation to find bijective proofs. So first construction were given by Cory Vauquelin, and then it really expanded with Gilles Schaeffer's thesis, and then developed a lot with many nice constructions. And so essentially these bijections explain the n to the -5/2 because essentially it's sort of between rooted maps and kind of unrooted trees. Well, to make it short, which can have some decorations, but essentially they are unrooted trees, and it explains the n -5/2. Also, it gives some nice direct proofs to the counting formulas. And also, well, it's already nice to have bijective proofs, but something really greater was that it opened the way to understand the metric structure of random planar maps. Okay? So by this, I mean you take a random map of size n, uniformly at random, and you want to say how it looks like. So what is the typical distance between two random points, the diameter, what is the order of magnitude? So, and thanks to this bijection, which heavily relies on the distance labels to associate a tree to the map, then people, probabilists, were able to show very deep and difficult results on scaling limits of maps. So the order of magnitude of distance is n to the 1/4, and the rescale, the metric space, converges to a certain random metric space, which is called so it's the Brownian sphere, I think now. It has changed the name. And so it's a very active topic of research, and there is also links to theoretical physics and also a very active domain called Liouville quantum gravity. So it's really very nice and a lot of progress recently. And so now, so maps are, I won't say it's all done, all is over and studied, but it's well understood. And so the interest has somehow shifted to decorated planar maps, so which are maps. So it's a pair made by a map and a certain structure on top of it. Okay, so you can choose. You can say it's a spanning tree, it's a Ising model, it's some orientation, Eulerian orientation, so what you want. And it will give different behavior. So There has been also some nice bijections in this domain. So compared to kind of pure maps, where the bijection is typically from maps to trees, here it's more from maps to decorated maps to walks, like walks in the quarter plane. So we will see some of them in the talk. And what is also nice is that now the polynomial, the exponent in the polynomial correction changes from model to model, so indicating different behavior. And so it's also linked to some theoretical physics parameters called central charge, which kind of indicates the behavior of the object when asymptotically. So then, yes, there has been a lot of work, but it's not solved. Like people expect to have a certain order of magnitude of distances determined by this parameter alpha. So the distances should be like n to the power f of alpha, and when alpha is 5/2, f of alpha is 1/4, as you have seen, and otherwise it's a different value. And so for now there are just some bounds on this how the kind of order of magnitude of distances, or how balls go around a marked vertex, how the exponent depends on this alpha. So there are just some bounds, but it's very active. Also, so for me, for this talk, I want to stress that this combinatorial structure gives some nice geometric representations of planar maps. So just take the example of Schneider-Woods, which are on triangulation. So it's some nice partition of the inner edges into 3 trees with which cross. So you can essentially there is one tree. Each tree flows toward each of the outer vertices like that, and it gives a famous planar straight line drawing algorithm for triangulation. So the idea is each vertex is placed using as a barycenter of the outer vertices, where the weights are given by counting faces in each of the 3 regions, which are delimited by the path from the vertex to the root vertex in each of the 3 trees. Okay, so for this vertex, you have the red path here, green path, red path, blue path. So it induces a partition of the inner faces. So here you have 4 faces. So the red outer vertex has weight 4/9, which is the total number of faces. And it turns out when you place vertices like this, you get a planar straight line drawing. Okay, so it's really a nice. There is some really connection with nice geometric representations. So for this talk, I will actually focus on 2 nice geometric representations. So they are not exactly maps, but we will see they are connected to models of decorated planar maps. So I will show how they can be amenable to some bijections, to walks, like walks in the quarter plane, as I mentioned. And I give some how it gives exact enumeration and also asymptotic enumeration, which is really important for the motivations I gave. Okay. So I will. I have to mention something that actually the results on corner polyhedra was a talk last year. So Erkan was giving the talk remotely, but he didn't make it to give the talk. So so I'm glad to have a kind of second chance to present with these results this year. I hope I will have time to take a bit to go a bit over these results on corner polyhedra. So we will see that they are really kind of closely related, even if on this picture it's maybe not completely clear. But okay, so we will see. So I will start with rectangulations. And so it's a very simple definition. It's just a tiling of a rectangle by rectangles. Okay? And you can see there is the question, if we allow points where 4 rectangles meet, which is called the degeneracy points. And if there is no such point, we say the rectangulation is generic. Okay? So, yeah, if I have time, I will talk a bit at the end on this, but for now, I will just consider generic rectangulation. And also as a kind of historic motivation, they are used in some called cartogram representations, which are, so this is from a census document, I think, for the US population in 1930. Okay, so it's not a research paper, it's really, and actually you can see the, actually, yeah, what you want is to represent, to have a map as a cartogram where the areas of the regions are proportional to some statistics. So, sorry, so here it's the population, it could be some other parameter. But you can see that having some simple shape for the faces makes it easy to sort of visualize how big the parameter. So, of course, now it's probably the map for this year is very different. So I don't know if there is one, but this is 100 years ago almost. So, okay, so it's just for history. So here I will be interested on the enumeration of such objects. Of course, there are infinitely many, so we have to define the kind of equivalence relation to make sense of counting them. So actually, there are two ways to define equivalence relations. We can consider strong equivalence relations, so which means that essentially, so you can see the important thing is to what we can call walls or segments, which are these they are horizontal and vertical segments which have contact. And we are allowed to slide walls, slide a wall along a wall. But when we have the strong equivalence relation, we want to maintain the adjacency of the regions. Okay? So for instance, this wall is allowed to move up, to slide up, but it cannot go, when we look at the strong classes, it's not allowed to go beyond this one. Okay? When it slides, it will stop a bit before, because we want to have this region adjacent to this one. Okay? So if it goes beyond, it's lost. So this is and another thing is that the order of contacts along a segment should be preserved. Okay, so this one comes first, this one comes second. For weak equivalence classes, we have more freedom. So we are allowed to move the walls along each side and without regard to going beyond this one. So this one is allowed to move to the far left side here. This one is also allowed to move down. Okay, so we have got more freedom. Okay. So it's also indicated by these operations here, which are allowed in the weak case, but not in the strong case. Okay? So also something to have in mind is that essentially a strong class is a weak class where you specified for each segment the shuffle order of the top vertical segments with the bottom vertical segment. Yeah?
So is it necessary that each segment has to touch a wall, or there can be internal segments?
That's a good point. So should each segment, yeah, so should each segment touch a wall? So you mean, could there be a segment such that at the end there is no contact? Yeah.
No, it touches another segment. So a segment which does not touch any of the walls.
Yeah. Sorry, that's a very small example. Yeah. It's in the bigger sizes, it's allowed. Yeah, thank you. So, yeah, you can have, so repeat, so you can have segments such as the two extremities do not touch the wall, any wall, okay? Okay, so now we have well-defined counting problems, so we can look at number of weak equivalence classes or strong equivalence classes, and the size, n is the number of regions. So to deal with the weak equivalence case, there is a nice convenient thing, which is the Schelling order. So it's quite simple. So you look at the top left region, and it's delimited by 2 walls, and you kind of push the shorter one. I mean, shorter in this sense, that it's blocked by the other one. And so you give a label n to this, to say it's kind of the last one, or the first one to be shelled. And you continue like this. So in this example, so this is the top left, so it's the label 7. Then you push this wall, this will be the next one. Then you will push this wall, this will be the next one. Then you will push this wall, and so on. Okay. So yeah, it's quite convenient to deal with the combinatorics of these weak rectangulations. Oops, sorry. And and also using this chain order, it's not too difficult to show that there is a for each weak rectangulation, there is a unique geometric representation which is called diagonal. So it means that the diagonal from top left to bottom right meets every region at a unit segment, say. And actually, the order is the one given by the Schelling order. And actually, to show the existence of this, you can use the Schelling order. Okay. So, but now what is nice is that we can use this representation to turn the rectangulation into a pair of binary trees. Okay. So we just cut along the diagonal. We obtain a pair of binary trees. So of course, they are highly correlated. Because the segments they cross straight at the diagonal, so they are correlated by the fact that if you look at the canopy word, meaning that each leaf either it goes right or left, and the canopy word for the top tree is consistent, matches the canopy word for the bottom tree, as can be seen. So there is a binary word associated. And actually, these twin pairs of binary trees, can be nicely encoded by a non-intersecting triple of lattice walks. So how does it work? So essentially, you treat the top tree. You will encode it by essentially, in the triple, the middle walk and the top walk encodes the top tree, and the middle walk and the bottom walk encode the bottom tree. Okay, so let's explain the top tree. So it's really a Narayana encoding, so really something classical. So you have so it's an encoding by a pair of words or of paths. So the bottom word is the canopy, gives the types of the leaves, okay, from left to right. The top word gives the types of the inner nodes from left to right. Okay. So as for leaves, inner nodes are of two types, whether the parent edge goes to the right or to the left. So you put a 0 if it goes to the right, you put a 1 if it goes to the left. And, well, it's not too difficult. It's an exercise to show that this encoding is a bijection when you formulate as paths with non-intersecting pairs of paths, like this. So they have to start, they have lengths maybe n-1, they start consecutive, say, they start at 1, 1 and 0, 2, and they end also consecutive. Yeah?
Yeah, just a question. It's a coincidence in this example, I'm assuming that this is a 3x3 path. As the size grows, how much long, which parts of the path, like what are the dimensions of the path you have?
Yeah, so what is the length of the path in terms of the size parameter? Yeah, so essentially it's number of leaves is the number of regions. Okay, so or number of unit segments here. So number of inner nodes maybe is the number of regions. So because you have one unit segment here for each region. So there are n regions, so essentially n is the number of nodes of each binary tree, and essentially it's the length of each walk. Yeah, yeah. And also, yeah, it's a bivariate counting that you have a parameter k that gives, say, a number blue segments, and n minus k will be number of red segments, something like that. Okay. Okay, so you have this Narayana encoding for the top tree, and you do the same for the bottom tree. So of course they share the same middle path. So what you get is a triple of paths that is non-intersecting. And it's well known that it can be continued by the Gessel-Vienno formula, and you get this nice summation formula. So it's it's kind of graded by this parameters that indicates how many east steps each of the three walks has. So they have the same number of east steps and north steps. Okay. So, but when you fix this number of east steps, you get a nice binomial formulas, and so you sum over all possibilities for the number of east steps. So this is called the Baxter number. It occurs really frequently in combinatorics. It counts many nice families. And the reason, so one family I will really insist on is plane bipolar orientations. And the reason why they are in Bayesian is essentially they have the same so-called generating tree. So it's a tree with all structures, and the structures of size n are at level n in the tree. And actually for rectangulations, to know the parent of an object in the tree, you precisely use this wall sliding to get the first step of the Schelling order. So, okay, so that's for the concept. Also, I mentioned this very nice result by Nathan reading on the link to the weak order on permutation. So it does it in two articles, in the weak and in the strong sense. And in each case, it gives a mapping from permutation of size n to rectangulations of size n, such that the pre-image of each rectangulation is a class, and so this gives actually a lattice congruence. Okay, and so actually this gives also a lattice on the set of weak rectangulations of size n or strong rectangulations of size n. So it's really nice. Okay, so now we have done the weak case, but still I want to give the model of decorated planar maps associated, since it's really very useful for the other models I will consider. So there are plane bipolar orientation, so there are acyclic orientation on maps with a single source and a single thing. And actually they are characterized by nice local conditions, which are shown here. So that at each vertex, you have a group of incoming and a group of outgoing edges. And sort of dually, each face, I forgot to put the arrows, but they are quite, it should be clear, that each face has a diamond shape, meaning it's made of a left path going on the left side and a right path going along the right side. And it will be very useful, this property of diamond shape of faces. So, so now we have a way to associate a plane bipolar orientation to a weak rectangulation. So the idea is to put a vertex in each horizontal segment, and for each region, you place an edge connecting the segment bounding the region down to the segment bounding the region up. Okay, so you do this for all regions, and you can see that what you get is a planar bipolar orientation, and actually you see well also this local condition of the bipolar orientations, that there are group of outgoing, group of ingoing, so they actually correspond to the regions on each side, and dually for the diamond shape of the faces corresponds to the fact that they are associated to vertical segments, as shown here. Yeah.
So where do you place the top and the bottom vertex?
So the question is, where do I place top and bottom vertex? So actually, you place them on the top segment. So it's not really relevant if you place it here or more to the left. It will give the same map. So it's not easy to draw in a really canonical, convincing way, but it doesn't matter where you place it on the segment. So Yeah, also a bit of history that this correspondence was used in the famous squaring the square problem, where actually, yeah, so the idea was to associate a square tiling. So now it's not rectangular tiling, but it's really a square tiling to each network, seeing it as an electric circuit. And actually, this gives, not a rectangular tiling, but where the regions are all squares, by where you compute the placement using the Ohm's laws. And also, so here it's really, and the idea was by doing exhaustive generation of networks to arrive to a network where the produced tiling would be such that all squares have distinct edge sides, and the bounding rectangle is a square. So it was the idea. But okay, so here it's a bit different. So in the sense that it's much more rigid to have square regions. Okay, so you cannot move like slide walls. You will lose having squares. Yeah.
So you're this on every horizontal segment.
Yeah.
The bottom and the top. How do you get the arrows?
How do you?
Where are the arrows coming from? Do you know which?
You mean the edges, or how do I put the edges? Yeah. So the question is, how do I draw the edges? So for instance, for each region, so say take this region. So there is the top boundary belongs to a segment. The bottom boundary becomes to a segment. So on this segment, there is a vertex. You have place, and so you put an edge connecting them. So it's a little confusing that you cannot draw the edge completely inside the region. So that's yeah. Okay. So it's also for history, but it's a bit different because it's much more rigid to have square regions. So actually, each network has a unique bipolar orientations for which the associated weak rectangulation has a representative with square regions. So it's a bit this kind of results, which can reflect this rigidity. Okay, so now I think I have to be faster because, So I will just mention, I will not detail, but I will mention that there is a nice bijection to another walk encoding of plane bipolar orientations by so-called tandem walks in the quadrant, which are walks with an infinite step set. So you have a southeast step, but you can allow all steps going to the northwest quadrant, steps of the form minus ij. And there is a bijection to encode plane bipolar orientations by such walks where, the starting and ending points are on the vertical and horizontal segment, and the position are kind of determined by which length you give the left outer length, the right outer length. So this is not really maybe the... But the point is that this encoding allows you to have a bijective, it's a bijective encoding of plane bipolar orientation, but it's much more precise in the sense that you control the types of the interfaces in the bipolar orientation, where the types is the pair ij giving the length of the left path and of the right path of the face. So it's really precise encoding. So I won't have time to detail, but let me just mention it's an iterative process. So from walk to bipolar orientation, you read the walk step by step, and you build your bipolar orientation. So essentially, when you read the southeast step, you maintain also a marked edge along the right boundary where things happen. So when you read the southeast step, this marked edge moves up, and when you read the step, these big northwest steps, like minus ij, you attach interface of type ij at the marked edge, and you update the marked edge to be the bottom edge of the face. Okay, so this is a simple bijection. I don't have time to really detail, but also it works. It gives a quadrant walk because there is an invariant that at each time, the current position, xy, corresponds to the length of these parts on the white outer boundary. Okay. So, and it's quite an exercise to see that this invariant is maintained by these operations. So, okay, so there are some rules to start and end. And here is a little example. So you have a tandem walk of length 5. You start from a path, and when you read a southeast step, you move the marked edge to the top. And when you read these face steps, which are going to the northwest quadrant from the current point, you attach a face. So here you have two faces, so you have two such face steps. Okay, but in a way, I will treat this bijection as a black box, so it's not really essential to understand, but it's simple, so it's nice to show it. Also, I can mention that there is a really simple bijection with these non-intersecting triples of walks. Again, I don't have time to detail, but essentially you read the middle walk of the triple, and you have vertical distance to the bottom walk gives the x coordinates, and vertical distance to the top walk gives the y coordinates in the associated quadrant walk, quadrant tandem walk. Yeah. Okay. So if I were to say, yes, they are called tandem walks. So you have this terminology, and yeah. So now we have this kind of diagrams of bijections obtained so far. So you have the weak equivalence classes. We had this encoding by non-intersecting triples of walks, but we can look at go via the model of decorated planar maps, which are plane dipole orientations. We have this encoding by tandem walks in the quadrant, and the two models of walks are consistent, so they are in bijection. But actually, it's really, oops. Now, for treating the other model, I really want to rely on this as a black box. So it's really a powerful bijection because it keeps track of the types of the faces. So it's really convenient. So each time we have structures modeled by, corresponding to models of decorated planar maps that involve plane dipole orientations, maybe with decorations on faces, then it will be can be treated with this bijection. So I will really be quite fast, but cover strong rectangulations. So compared to the weak case, it's more difficult. So we don't have like this diagonal representation. We don't have a canonical geometric representative. So the strategy is to go to the model of decorated planar maps. So it works by taking the dual. Okay, so as we saw in Colin's talk, so we put a vertex in each region, and we put an edge for adjacent region, and also we put some colors and directions to these edges. Okay, so essentially we have the red edges that flow from bottom to top, and the blue edges that flow from left to right. Okay, and what we obtain is a triangulation of the foregone. With we partition of the inner edges into two bipolar orientations. So one that flows from bottom to top and one that flows from left to right. Okay. Also, something nice is that this structure is actually characterized by these local conditions here. This one at inner vertices, this one at outer vertices. And they are enough to imply that the two orientations are acyclic. Okay. So it's quite convenient. And so now the strategy is to break the symmetry between the red and the blue color. So to see really transversal structure, so these decorated maps, as the red bipolar orientation with decoration in the faces. So we essentially treat the blue edges as decoration, so they are kind of, we have to choose for each red inner face how we place the blue edges transversally. Okay. So and what is nice is that this number only depends on the type of the inner face, which is controlled by this KMSW bijection. And it's just a binomial coefficient. So it's really very simple that we want to count the number of ways to add transversal edges to two parallel paths to form triangular faces. So it's really just a binomial coefficient. But now it gives a way to count these strong rectangulations. Okay, so by the KMSW bijection, they correspond to these tandem walks where you just put a weight on each phase step. So minus ij, we put this binomial weight to account for a number of ways to place the blue edges inside. Okay. So it's really simple. So it's not explicit in the sense you have a nice counting formula, but at least it gives, we can write some recurrence to compute the numbers. Also, something nice to make the recurrence simpler is that actually the weights can be encoded by replacing a big step by a portion with small steps. Okay, in this way, so it's again very simple. And we have a reformulation as walks with small steps. Gives some explicit recurrence, so these are the first coefficients. And actually there is another method, which it's maybe not so well known, but very nice. And another model of walks with small steps by a group of Japanese researchers. And also a recurrence. It's also a model of walks in the quarter plane with small steps, but of different shape. Okay, so I have 8 minutes, so I'm sorry, I will be very fast. So actually, even if we cannot solve the counting problem, we have a recurrence for strong rectangulations. So for the weak, it's solved in the sense we have this nice formula with the Baxter numbers. But what is nice is that there is an automatic method, the probabilistic method, to compute the asymptotic estimate for number of walks in the quadrant, say starting at ending at the origin or at prescribed points. And it relies on a very nice probabilistic result on the kind of asymptotic polynomial correction for the exit time of a walk in a cone of angle theta. So we have this nice this nice formula, and also a formula. So this is we have the formula for exit time at least n and returning to the origin at time n. So we have this also this estimate. This is the one we use because our walks, they are excursions. So essentially they start and end at the origin. And from this, all our estimates are of this shape. So we have the exponential growth, and the polynomial correction is of the form 1 plus pi over arc cosine of simple rational number. So for the Baxter case, it's all computable by the formula, the summation formula, but it's also doable by this method. We get 4. But for the strong case, it's more complicated. So the cos of theta is 7 over 8. So what is also very nice is the exponential growth rate is this simple rational number, which is not guaranteed. So from the method, it's clear it will be an algebraic number, but getting a simple rational number was nice. And but the alpha is not rational, and so the generating function is not defined. So we cannot expect to have a nice formula as in the Baxter case. Also, let me mention that this 27.5 has a nice interpretation with this other encoding by the same group, with a different order on the authors, but they are the same group. So. And yeah, I won't have time, but yeah, I mean the slides are on Discord, so you can look at how it works for the case of small steps. Essentially, the idea is to compute this angle theta. You have to compute the covariance matrix, and you want to make it the identity, and you use a shear transform to turn the step set into a step set with where the covariance metric is the identity, and the opening angle you obtain is gives the asymptotic, the polynomial exponent. Okay, so I have 5 minutes for the results of last year, so, so it's 5 minutes talks for the. Okay, so I will talk about this corner polyhedra. So actually, to motivate this, I mean, to relate it to what I showed before, I can introduce them by talking about a natural extension or to the tricolored case. So we want to look at now contact systems of three kinds of segments with three slopes at 60 or 120 degrees. And with contacts like this. So I mean, each contact is two segments on one side meet a point inside another segment, like this, okay? Again, we have a notion of generic and non-generic, where you have a point of degree 6. But it's a bit similar to what we had with square tiling. So, okay, so here the regions have to be equilateral triangles, so it's very rigid. So it's not very satisfying to get counting problems similar to what we had before. And so to kind of remedy this, we relax the problem. So instead of forcing segments, we just say they are curves. And it's a more topological way to look at these contact systems. But still, we want to have contacts as before, and okay, so again we'll have these walls, we'll have these contacts on each side, but now a contact will be made by two segments meeting at a point, and again we'll have a strong version where we can slide these contacts, but keeping the adjacencies between regions, or a weak version where they can slide independently on each side. So again, we have two counting sequences. Yeah, so for the bicolor case of before, it was the same of looking at the relaxed version or the version with segments, but here it's really different. And then they are actually in bijection with this corner polyhedra, which is a kind of topological version of plane partitions seen in 3D. Okay, so it's a kind of a boundary surface made of flats which are orthogonal to an axis, one of the three axes. And as in a plane partition, you have three flats pointing backward and all the other flats pointing upwards. So now the volume, we don't count them by volumes. It's not well defined, okay, since we consider them up to moving flats. So flats are a bit like walls before. And so now the size is the number of flats, okay, -3. And we have a bijection with these weak contact systems. So it goes like this, so it's quite simple. You have segments for each flat and contact for each point. And the kind of the curve that receives the contact is the flat forming an elbow at the point. So it's, yeah, there is a simple bijection. We have a model of decorated planar maps for this. It can be directly done from the contact system, but it's quite simpler from the corner polyhedron. And it's, again, by a duality, so you place a vertex in each flat, and you place an edge for each adjacency between flats. So what you get is an Eulerian triangulation. You have, Eulerian triangulations are known to be three-colorable, and the three colors corresponds to the three types of flats. Okay. And yeah, essentially, this combinatorial structure is a kind of three bipolar orientations that are superimposed. But what we sort of showed is that it's quite easy that we can just retain all the information by just keeping one of the three bipolar orientations, say the one flowing from left to right, and it's enough to encode the whole structures. And actually, we also check that this bipolar orientation is characterized by simple local conditions of forbidding transitive edges I mean, yeah, forbidding, say, faces with only with the left boundary as size as length 1 if it ends at if the top vertex is black, and a similar condition if the top vertex is white but it's on the left side. So I'm really yeah. So I can just finish saying that it gives a model of quadrant tandem walks, but with a bimodal condition, meaning that the step set depends on which sublattice you sit at. So you have a lattice, even sublattice where x plus y is even, odd sublattice where x plus y is odd. And yeah, depending if you are at even or odd, you can use vertical segments or not, and same for. So it's written here, but the important thing is that you have this further ingredient that you have a bimodal behavior. So it's a little more involved than the case of rectangulations, but it's still, we can write some recurrencies and have a quick computation method. So we have something similar with a strong case, but again, as in the rectangulation case, you have some weights on the faces to account for. So actually, you delete one colors in your bipolar orientations, and it accounts for binomial weight inside faces. So it's really similar to what we had before, but with a bimodal condition. And yeah, then we can do the same asymptotic method by this result by Denisov and Vartel using probability. And what is nice is that even if it's quite more involved with this bimodal condition, we still have simple rational values for the coefficient, for the constants in the asymptotic estimate. So like the exponential growth rate is again a simple rational number, and the alpha you have pi over r cos of simple rational numbers. Yeah, so it's a bit yeah. I mean, the method would have to be extended to the bimodal setting to have really this as a theorem, but yeah. And yeah, I just flashed this, but I will not talk about it. Yeah, thank you.
So, thank you very much. So we have time for 1 or 2 questions, if there are.
So is it possible to extend your method for the first problem to the non-generic case by controlling the number of points where you have this plus?
It's here.
No, for the rectangles.
So is it not the thing at the top?
Oh, this is exactly that. Okay.
Thank you. Yeah. So.
Another question?
Can one say anything about, say, how many strong classes correspond to each weak? Maybe I said it backwards. Can one relate the weak and the strong enumerations in any way? Say, maybe fix a weak equivalence class and ask how many strong equivalence classes go with it.
Yeah, so this is sorry. So if you have a weak equivalence class, can you show how many strong classes are falling in this? Is it? Yeah. So actually, it's a product of binomials. Okay. So for each segment, you have to determine the shuffle order of the contact. So say if you have k on one side, L on the other side, it would be binomial k plus L k for each segment. And then you have to multiply all these binomial coefficients. And it gives you the number of strong classes for this weak class. Yeah. But this is not what I use for counting strong classes. I was really breaking the symmetry between red and blue. But still, yeah, for a given weak class, it's really.
And is it similar for
Yes. Actually, here for this, it's really again for each one you have a binomial with a number of one side, number of the other side. So it's similar.
Okay, so let us thank Eric for his talk.